Today's speaker is Damián Pitalúa-Garcia. Damián did his PhD at DAMTP in Cambridge under the supervision of Adrian Kent. His thesis was entitled Quantum Information, Bell Inequalities, and the No Signaling Principle. Damián then did a postdoc at the Free University of Brussels in the Laboratoire Information Quantique lab. And then Damián continued his European tour and did another postdoc at the University of Paris. And now Damián is back at DAMTP as a postdoctoral researcher funded by the UK Quantum Communications Hub. And Damián is a world-leading researcher on quantum communication and secure tokens. So we're therefore extremely happy to have you on the call today, Damián, to hear about the state-of-the-art research that you do on this topic. So thanks for joining us, and the virtual floor is yours.
Well, this presentation is divided in two parts, and is work in collaboration with Matthew Bosio, Adrian Caballes, Eleni Diamanti, Adrian Kent, David Lowndes, and John Rarity, and it is work funded by the UK Quantum Communications Hub. So first I will talk about multiphoton and side channel attacks in mistrustful quantum cryptography. Mistrustful quantum cryptography is a large field and one of the major applications envisaged for a global quantum internet. It includes various important tasks. In this paper, we identify new multiphoton attacks on practical implementations of mistrustful quantum cryptography with photonic setups and show that some previous implementations were vulnerable. I'm gonna describe the task using this setup. This is a photonic setup where we have two parties, Alice and Bob, who do not trust each other, but they collaborate to implement the cryptographic task. So many interesting protocols in mistrustful quantum cryptography use some version of this task. First, Alice sends Bob a random BB84 state. In this setup, this is achieved by encoding the state in some photonic degrees of freedom, for example, polarization. Then Bob generates a random bit, beta, privately and measures the received state in one of the two bases. In the setup, he performs that by rotating the wave plate to one of two positions. And Bob uses two single photon detectors, which are threshold, meaning that they cannot distinguish the number of photons in the pulse activating a detection, activating a click. Bob then sends a bit message to Alice reporting whether a measurement outcome was produced, the case m equal 1 or not, the case m equals 0. We want to consider security against Alice. This is the property that the probability that Alice guesses the bit beta should be arbitrarily close to 1/2. Here, we assume that Bob is honest, meaning that Bob follows the protocol, the agreed protocol, but Alice may deviate arbitrarily from the agreed protocol. Security against Alice can be achieved in ideal settings where step 3, communication of M by Bob, is not needed. However, in practice, there are losses in the quantum channel. The detectors do not have perfect efficiency and other imperfections. There are also other imperfections, and this implies that Bob needs to communicate the successful measurements to Alice. So Bob needs to report losses to Alice. And this opens up security problems because now Alice can obtain some information about the bit beta from Bob's message. So Therefore, Bob needs to be careful in choosing his reporting strategy. How is Bob going to report a successful measurement to Alice? I'm gonna describe various reporting strategies by Bob using this setup. And
just to interrupt you, Damián, I had a question in the chat.
yes,
Where someone asked, could you describe what the idea of beta is? What does beta do for the sake of communication in this protocol?
okay, yeah, good question. Well, this task is it works mainly as a subroutine for other more complex tasks, right? So in general, what beta does is beta encodes Bob's secret data in this more complex protocol. So Alice has some secret data which she encodes in the quantum states that she transmits to Bob. And Bob will encode his secret data by choosing, in this case, one of two measurement bases.
Okay.
Yes, thank you for that question. So multiphoton attacks, we define them as any strategies that Alice uses by preparing a photon pulse, which can have an arbitrary number of photons and can be in an arbitrary entangled quantum state, sending this to Bob, and then using Bob's message to obtain some information about Bob's bit, which ideally should be secret. So it's a broad class of attacks, and I'm gonna now discuss some reporting strategies by Bob and the multiphoton attacks that arise in those strategies. So a simple strategy by Bob is to simply report single clicks to Alice. So this means that if Bob obtains clicks in both of his detectors, he will discard this. He won't report this as a valid measurement to Alice. This allows Alice to implement this attack that we call multiphoton attack 1, considering the ideal situation in which there are no errors and Alice's and Bob's measurement bases are perfectly aligned. The attack works as follows. Alice sends Bob a photon pulse with a large number of photons in the same BBT4 state. If Bob measures in Alice's bases, then only one detector click because they are perfectly aligned. Otherwise, if Bob measures in a different basis, because Alice is sending a large number of photons, this means that a large number of photons will go to one detector and also a large number of photons will go to the other detector. So both detectors will click with high probability. This means that because Bob sends the message m equal 1 only if one detector clicks, Alice then learns whether Bob measured in the same basis that she or in the other basis, so Alice learns the value of beta. In a more realistic situation in which we have errors and misalignments in the bases, we still have some property like this. Alice can still guess Bob's bit with high probability, and we have simulated this in an experiment. This was performed in Paris by our colleagues Matthew Bosio, Eleni Diamanti, and Adrian Caballes. We see that the experimental dots are very well aligned to the theoretical expected values, and Alice can guess Bob's bit with high probability by increasing the average photon number of Alice's pulse. So this is an attack that can be implemented in practice. So for this reason now, we consider a different reporting strategy. Now Bob will accept as valid measurements those in which at least one detector click, not those in which only one detector click as in the previous strategy, but in which at least one of them click. And importantly, we have shown that if Bob's detector efficiencies are exactly equal, then this protects him against arbitrary multiphoton attacks. So Alice can send an arbitrary pulse with any number of photons in an arbitrary state that can be arbitrarily entangled. If Bob applies this strategy and his detector efficiencies are exactly equal, then Alice cannot learn any information about the bit beta from Bob's message. Unfortunately, in practice, we cannot guarantee the detectors to have exactly equal efficiencies, but attenuators can help to reduce their difference. So now we define multiphoton attack 2 as strategies applied by Alice in which she exploits the difference in detector efficiencies when Bob uses reporting strategy 2. Or more broadly, when Bob reports as valid measurements those in which both detector click with unit or high probability. So we are a bit broader than reporting strategy 2 because we allow a high probability of reporting double clicks, not necessarily exactly unit. Another strategy is symmetrization of losses. This was introduced in this paper. And here, Bob discards detection events from the most efficient detector or basis, aiming to equalize his reporting probabilities. We have shown that this can offer very good protection to Bob if Alice's pulse has 0 or 1 photon, and if Bob's darken probabilities are small. The problem with this is that Alice can be dishonest, so Alice doesn't need to follow the agreed protocol with Bob, so she doesn't need to send a single photon pulse as agreed. She can send an arbitrary multiphoton pulse, and therefore the claim security of symmetrization of losses does not follow. This is important because various important experimental demonstrations of mistrustful quantum cryptography have used symmetrization of losses and have claimed security based on this, but this argument is not well supported. We also consider more general reporting strategies that we call probabilistic reporting strategies, where Bob sets the message m = 1 with a probability that depends on which detectors click and on Bob's measurement basis. We see that the previous strategies are special cases of these probabilistic reporting strategies. And another particular strategy is the trivial one, in which Bob accepts as valid measurements all detection events with the same probability. So, for example, he can simply accept all detection events as valid measurements, and this basically says that the message m is fixed. So he's always sending m = 1. So this cannot provide any information to Alice because this is fixed for any basis and for any detection events. So this offers perfect protection against arbitrary multiphoton attacks. And in fact, it is the only known reporting strategy guaranteeing this perfect protection. The problem with this strategy is that it requires extremely good setups. It requires the losses to be very low and also very high detection efficiencies so that the protocol can work even if Bob is accepting all measurements as valid.
I have another question here in the chat.
Yes.
On this paragraph you just showed us. So someone asked, can you give us some more intuition about why low losses and high detection efficiencies have to be in place? I think you've already touched on it, but so they say in this fixed probability example, can you give us some more intuition of why we require low losses and high detection efficiencies?
Yes, yes, that's a good question. Thank you. Well, as I said, this task works as a subroutine for more complex tasks. In these more complex tasks, usually what we need is that when Bob measures in the same basis of preparation by Alice, we expect that Bob gets the outcome corresponding to Alice's encoded state, right? Because, for example, Bob might have to report to Alice later in this more complex protocol. He might need to report to Alice the outcomes, and Alice will tolerate only a small fraction of errors, right? So if the losses are very high, this means that, and Bob accepts all measurements as valid. This means that for a great fraction of pulses, Bob is accepting measurements where he doesn't have an outcome. He doesn't know what the outcome is. So he will have to guess what state Alice encoded. So there will be a very high probability of error, and therefore Alice will not accept Bob's outcomes as valid.
Okay, thanks. That's clear. Thank you.
So I give a very brief summary here of multiphoton attacks 1 and 2. We said the first one applies when Bob accepts double clicks as valid measurements with 0 probability or with a small probability. A proposed countermeasure is then reporting double clicks with unit or high probability, or using the trivial reporting strategy if possible. Then if Bob reports double clicks with unit or high probability, then we are in this situation. In the realistic case in which Bob's detection efficiencies are not equal, then this opens up the possibility of other type of attacks that we call multiphoton attack 2. And the countermeasure is then making Bob's detection efficiencies exactly equal or sufficiently close, or using the trivial reporting strategy if possible with the experimental setup. And our main result is that in the realistic case in which Bob's detection efficiencies are different, the only probabilistic reporting strategy that guarantees to Bob perfect protection against arbitrary multiphoton attacks is the trivial reporting strategy, meaning the strategy where Bob accepts all measurements as valid. This has the important implication that the symmetrization of losses strategy that we mentioned, introduced in this paper, does not guarantee the claim protection, and this has implications for various experimental demonstrations that have used symmetrization of losses and therefore cannot guarantee their claim security. Here we have a list of some previous experimental demonstrations of mistrustful quantum cryptography that are subject to our multiphoton attacks. So they are all subject to the second type of attack, and this one is covered against attack 1 because they report multiple clicks. Some others do not clarify whether they reported double clicks, and so we don't know whether they're covered against attack 1. This use setup 1 that we described with 2 photon detectors, and here this use a slightly different setup with 4 detectors, but the analysis can be extended easily to this case, as we do explicitly in our paper. So to conclude the first part, in multiphoton attacks, dishonest Alice sends multiphoton pulses and obtains information about Bob's measurement basis. The trivial reporting strategy, where Bob does not report any losses, is the only known perfect protection, but it requires state-of-the-art experimental setups to be useful in practice. There are other countermeasures that can be investigated, but as we discussed in our paper, these open other problems. We also analyze a setup with 4 detectors, and our analysis extends easily to this case. There is also another type of attacks called side channel attacks, where Alice controls degrees of freedom that were not previously agreed with Bob for the transmission of the quantum states. So these degrees of freedom could be, for example, special degrees of freedom, for example, the angle of incidence in the channel. It could be time, the time at which Alice sends the photon pulses. It could be light reflected from Bob's setup. It could include a wavelength of the photon pulses, etc. So there are various degrees of freedom that Alice could exploit to gain information about Bob's basis. And there is not currently any perfect protection against this, against arbitrary side channel attacks. A countermeasure that can provide unconditional security in principle is for Bob to use teleportation to filter Alice's signal. So here the idea is that Bob prepares a pair of entangled photons and uses one of these to apply the teleportation protocol on the quantum state received from Alice, and Bob sets the other photon in a secure laboratory, so the quantum state can be teleported securely to this laboratory. The problem, a potential problem here, is that in practice, when Bob tries to generate a pair of entangled photons, he will generate more than one pair with some non-zero probability, and so this could, in principle, open some security problems. So we believe this strategy requires further investigation. So with that, I conclude the first part. I can take questions now if you wish, or I can move to the second part.
I have one question in the chat, maybe. Let's see. It's 2 questions in the chat, actually. So someone is asking, what do you think? Is there any hope for an actually fully secure quantum communication protocol in the future? Are you positive or skeptical towards this?
Yes, that's a very good question. I think it's very difficult to say there will be perfectly secure implementations, right? Because there are various practical issues that have to be considered. But this countermeasure that I just mentioned, I think is possible. So this might be a good way to provide, let's say, very good security. Unconditional security is a very strong word, but it's yeah, it's encouraging. It's encouraging, and yeah, that's what I can say.
Okay, and the second question is, can you use several protocols like your setup in parallel and then somehow combine them via majority voting or some other encoding to achieve better security in a way that's similar to quantum error correction or other such ideas?
Yeah, that's a good question. Yeah, I haven't thought about that possibility. As I said, this task can be used as a subroutine in more complex tasks, and implementing this in parallel is certainly a way to do that. Because actually, more generally, Bob will not only have a bit of secret data, he might have many bits. So we might want to implement this in parallel. The particular idea of using majority voting, I'm not sure at the moment whether this can give any advantage. Yeah, I'll have to think about it, but it's certainly a good idea to explore.
Maybe topic for future ideas. I have another question here from Kieran Dalton. Kieran is asking, what are the state-of-the-art detection efficiencies and how high do they have to be for the trivial method to work?
Oh yeah, that's interesting. I think there have been experiments reporting very high detection efficiencies, I think of the order of 90%, and also very high fidelities of, let's say, 99%. So with these values, which are challenging with standard setups, but are possible because I have read papers reporting these values. The trivial reporting strategy could work. It will all depend on the specific applications, the specific tasks, the specific more complex cryptographic task which we are considering. But I think this would work for many practical applications. And in fact, it's something we are exploring in quantum tokens. Is the second part of my presentation. So I think we might be able to use the trivial reporting strategy.
Okay, cool. Thanks, Damián. I think the questions for now are finished, but okay. So yeah, this is probably a good time to move on to your next part. Thanks.
Thank you. So now I will talk about practical quantum tokens without quantum memories and experimental tests. This is work in collaboration with Adrian Kane, David Laus, and John Rarity, and also funded by the UK Quantum Communications Hub. Quantum tokens is the first invention of quantum information science, invented by Wissner in 1970, but published in 1983. In Wissner's quantum money schemes, the bank gives the user a serial number S and quantum states generated randomly from some set of non-mutually orthogonal states, for example, BBT4 states as illustrated here. To access a resource, then the user gives the serial number and the quantum states to the bank, or alternatively, a verifier knowing the serial number and the quantum states asks questions to the user about these quantum states. The no-cloning theorem and other quantum principles imply that the user cannot fork the quantum tokens. However, their implementation is not presently practical because they require quantum state storage in quantum memories and or long-distance quantum communication, which are quite challenging technologies at present. Some properties of quantum tokens are unforgettability, meaning that the user cannot have a token be validated more than once. User privacy, the user can choose privately when and where to present the token. And instantaneous validation, meaning that the quantum tokens can be validated near instantly without cross-checking, meaning without communication delays. It is a crucial point to notice that there exist simple, purely classical token schemes satisfying any two of these three properties, but not the three simultaneously. So the advantage of quantum tokens over standard classical token schemes is that they can guarantee the three properties simultaneously. So here I give a simple example of a classical token scheme that satisfies the two first properties, but not instantaneous validation. The bank gives a classical password X to the user. The user then simply needs to give the password back to the verifier to access the resource. But the verifier first communicates with the bank, who then replies saying whether the password is correct and also whether the password has not been presented before. So in this example, the first verifier will validate the token and will give the resource to the user. But the second verifier, here the user is trying to cheat and gives the password to two verifiers. So the second verifier will not accept the token because the bank will say that it has already been presented, right? So it's a very simple scheme satisfying unforgettability and user privacy, but not instantaneous validation because there is a time delay in communication between the verifiers and the bank. And you might say, well, what's the problem with such a delay? If the bank and the verifiers are restricted to be on the Earth's surface, we could have the verifier in one antipodal point and the bank at the other, at the antipodal point, sorry. And using communication at the speed of light, this could take a few milliseconds. So you might say, why do we care about a delay of milliseconds if in practice, when we made bank transactions, we can take even a few seconds and that's not a big problem, right? Well, there are some situations where short time delays are crucial. For example, in financial markets, there are high frequency trading transactions which take place within half a millisecond, for example. So in this kind of situations, we would like to avoid these short time delays. So instantaneous validation might be a very valuable property in those scenarios, as well as unforgettability and user privacy. The disadvantage of quantum tokens, of standard quantum tokens, is that they are not practical because they require quantum state storage and or long distance quantum communication. This implies that a full experimental demonstration of a quantum token scheme remains an important open problem. However, S-money schemes have been invented recently by Adrian Kent, and these define secure quantum tokens without needing quantum memories or long-distance quantum communication, and are therefore practical with current technology. Applications of S-money, like quantum tokens in general, as I mentioned, are in scenarios where relativistic constraints are important, for example, in high-speed transactions in financial markets. I will present theoretical and experimental results, suggesting that a full experimental demonstration of quantum S-money tokens, and therefore of quantum tokens in general, can be implemented in practice. So I will first present a simple quantum S-money token scheme, not requiring quantum state storage or long-distance quantum communication. Then I will present our extension that increases the flexibility in space-time for token generation and presentation, and that also allows for various experimental imperfections, as well as experimental tests of the quantum stage of our schemes. So in this quantum S-money scheme, we have two parties, Alice, the acquirer or user, and Bob, the bank. They agree on space-time presentation points, QI, where Alice can present the token to Bob. And the scheme works as follows. Bob gives Alice a token of n random BBT4 states within the intersection of the causal path of all the presentation points. Immediately upon reception, Bob measures the quantum states in a basis DB that depends on the chosen presentation point QB. So we see that there is no need for quantum memories because measurement is immediately upon reception. And from this point, everything is classical processing and classical communication. Therefore, there is no need for long-distance quantum communication either, because this quantum communication from Bob to Alice is short range. It can be or between adjacent labs separated by, say, a few centimeters or so. To present the token, Alice gives the classical outcomes X to Bob, and then Bob validates the token by checking whether these are consistent with having measured the transmitted quantum states in the basis DB associated to the presentation point QB. Okay, properties satisfied by this scheme are unforgettability, as we can show that the probability that Alice can make Bob validate tokens at 2 or more presentation points decreases exponentially with the number of transmitted qubits. User privacy, because Alice doesn't need to give any information to Bob until her chosen token presentation point. And instant validation, because Bob can validate the tokens near instantly. In particular, he doesn't need to wait for messages coming from other agents at space-like separated token presentation points. And again, an important property of this scheme is that we don't need quantum memories or long-distance quantum communication, and therefore is practical with current technology. Now I outline an extension of this scheme, which extends the flexibility in space-time for token presentation and validation, also satisfies unforgettability and privacy, considering various experimental imperfections under standard assumptions in practical mistrustful quantum cryptography. And it offers protection against arbitrary multiphoton attacks that we discussed in the previous part of the presentation, to guarantee privacy, assuming detectors having equal efficiency. This is an assumption that, as I mentioned, cannot be guaranteed perfectly, but it is a step forward in considering protection against multiphoton attacks. Here, I'm going to discuss the case of 2 presentation points, but our schemes works for arbitrary number of presentation points. This scheme works in 2 stages. In the first stage, we have short-range quantum communication, which can be arbitrarily slow and can be completed arbitrarily in the past of the presentation points. So this communication part, this quantum communication part can take, for example, hours or days, and can be completed, let's say, days in advance of the presentation point. So this is very flexible. We then have a second stage, which is purely classical, this part. And in practice, we need some of these computation and communication steps to be very fast. Because as I mentioned, in order to have an advantage over simple classical schemes, we want to have at least 2 spaceless separated presentation points. So, for example, if these presentation points were separated by a distance of 300 kilometers, because light takes half a millisecond to go from this location to the other one, we want the communication and processing of information here in the validation stage to be completed within half a millisecond. So to implement this in practice, we need sufficiently fast field programmable gate arrays, synchronized to a common reference frame, using, for example, GPS devices and atomic clocks. This is a problem that we are discussing with experimental colleagues. So our scheme considers various experimental imperfections. For example, we allow Bob's states not to be perfect BB84 states. We allow a fraction of Bob's states to have arbitrarily high finite dimension instead of in qubits. This is to consider the property of single photon sources that they necessarily emit multiphoton pulses with non-zero probability. We also assume we also consider probability distributions that are not perfectly random. We allow losses of the transmitted quantum states. We allow a fraction of errors in analysis measurement outcomes. And in photonic setups, we also allow the single photon detectors to be threshold, meaning that they cannot distinguish whether a click, they cannot distinguish the number of photons in the pulse activating a detection. That's the threshold property. And we also allow non-zero Darkham probabilities. So we perform experiments of the quantum stage of our scheme. This was implemented by David Lowndes in the University of Bristol with this photonic setup that he designed and constructed. Here we have Bob's device transmitted quantum states to Alice in polarization degrees of freedom. Alice measures the polarization using polarizing beam splitters and single photon detectors. So in our experimental test, we generated 40 million quantum states in 4 seconds, achieving an error rate of approximately 6% and a detection probability of approximately 2%. And we obtain these deviations from the random distributions for the basis and state generation. Our results are encouraging. They show that with minor refinements of our setup, we could guarantee security. So here we have the experimental plot, and this red dot represents the assumed uncertainty of 10 degrees in the block sphere. Our experimental values for the deviation from the random basis generation and state generation are 24 and 36 times 10 to the minus 4, so they are well above the plot. We would need this to be below the plot to guarantee security. So we didn't guarantee security, but if we decrease, for example, the error rate to 3%, and we decrease the uncertainty angle theta to, let's say, 3 degrees, we would be on this yellow dot. And in this case, by decreasing these values by a factor of 10, we would be below the dot, and so we would guarantee security. So in summary, with minor refinements of our setup, which seem possible, which seem quite possible, we can guarantee security in our schemes. So now I conclude. S-money token schemes provide instant validation, user privacy, and unforgettability, and do not require quantum state storage or long-distance quantum communication. We extended a previous quantum S-money scheme to a practical setting, considering various experimental imperfections, and we proved its security. Our experimental test of the quantum communication stage show that with minor refinements, we could guarantee security. And we are assessing the practicality of a full experimental demonstration with space-like separated token presentation points. With that, I conclude this second part of the talk. I just have another slide. So I would like to present that very quickly. This is a problem that we are investigating at present in collaboration with Adrian Kent and with various others colleagues in the quantum communications field. The problem is the following. This is quantum position authentication. Bob wants to prove his location to Alice using quantum physics and relativistic signaling constraints. So Alice has various agents surrounding Bob, and the protocols, the schemes work by transmitting and processing classical and quantum signals. It has been shown that unconditionally secure quantum position authentication is impossible, but an open problem is to demonstrate quantum position authentication schemes under different security models. And this is a problem that we are considering. Some practical problems include secure synchronization of reference frames and fast processing of classical and quantum signals using, for example, field programmable gate arrays. So with that, I conclude my presentation. Thank you.
Thanks a lot, Damián. This was super interesting. It's a long time since I studied kind of quantum cryptography, so a lot of things have happened since I took my undergraduate courses on it. I have one question immediately in the chat on the tokens. So someone is asking, you say that these are okay in relativistic models. Are they also okay in general relativistic models where maybe your light cone tips to one side?
Yeah. So I'm not sure if I understood correctly the question, but let me comment on this. our schemes have an advantage over purely classical schemes in relativistic settings where short time constraints are important. But the security does not rely on any relativistic constraints. So in fact, we could have time-like separated presentation points and our schemes would still be secure. That I just wanted to clarify that might be
Okay.
something related to the question. And the other possible issue is this could work in a more general spacetimes. I don't know if maybe that was the other part of the question. So the only property we need is that the presentation points have to be spatially separated. So we don't need this to be in a Minkowski spacetime. It can be in some more general spacetimes where we can guarantee spatial separation of the presentation points. But because we want to focus on realistic scenarios, we only consider spacetimes that are close to Minkowski, so like near the Earth's surface, things that we can actually implement in like now or in the near future, right?
Okay. I have another question here on this quantum position authentication. So someone asked if you can elaborate on why it's been proven that unconditional security is not possible.
Yes, yeah, that's a good question. The attack is broadly as follows. If wants to impersonate Bob, so that if can communicate with Alice and make Alice believe that Bob is at the required location, right? While if might actually have moved Bob somewhere else. So Bob in practice can be some object that is very valuable to Alice, and Alice wants to keep in a specific location. So if I want to move that object and make Alice believe that the object is still there. So what if can do is she can have various agents intercepting the signals that Alice sends to Bob. This can be classical and quantum signals. And if can have enough entanglement share among their agents. So then by intercepting all signals and sharing and using this entanglement, if can apply what is called an instantaneous non-local quantum computation or instantaneous non-local measurement, which basically allows if to implement whatever quantum computation or quantum measurement Bob was supposed to perform on the signals received from Alice. If can do that by performing some instantaneous non-local quantum computation and including some communication steps, right? Because this cannot be actually instantaneous. That's the name that it cannot be instantaneous. It requires some delay to communicate so that this is consistent with the relativity. But this time delay is the same that Bob would have needed to communicate the information back to wherever Eve's agents are. So that's the way that these attacks work. And so the idea is that if Eve has enough entanglement, she can always implement whatever quantum computation or quantum measurement Bob was supposed to perform at that location. And so therefore Bob might be somewhere else and Alice might still approve the received responses as valid coming from Eve, in fact, not coming from Bob.
Okay. Well, thanks a lot, Damián. I think we've done our hour now. Is there any quick final question from anyone? I think that seems to be all the questions. So thanks again. Thank you, Damián, and to everyone on the call. This was the last seminar series of this academic year. There might be some additional seminars organized over the summer. So keep checking your emails, but otherwise we will see you when the next academic year starts.